In the other talks this series, I've been talking about the insides of bodies, how the way they're built up inside affects their properties. In this one, I'm taking quite a different theme, the surfaces of bodies, the properties of surfaces. Surfaces are the boundaries where matter of one kind meets another, like the surface between a solid and a liquid, or the surface where two liquids touch each other, or the surface, say, between a liquid and a gas. And we are going to talk about the nature of these surfaces and see how we can explain some phenomena by these properties. Now, I'll start with a very common experience, which most of us are very accustomed to nowadays, washing up. Now, you know, when you're washing up, if you just use plain water, it's quite easy to clean a jammy plate. But if you have a buttery or a greasy plate, it's very much easier if you put a little detergent in the water. I've got a good old greasy, dirty plate here. Now, if I rub it hard, of course, even with water, I can rub off a good deal of the mess onto the washing up cloth. But that's not a thing that's very much, it was rather frowned on in the home. And really, you see, I'm mostly, when I rub this here, just moving that muck from one part to another. But if I take it and put a spot of detergent on it, I can get a really nice clean plate, thing you're all very familiar with. We get absolutely spotless, like that. So that detergent seems to make a vast difference. Why? And really, as we're going to see, that's going to be a property of surfaces. We'll talk first about the simplest kind of surface, the surface of a liquid. Liquids behave as if they had an elastic skin round them. We've got a funnel here with some oil in it. This oil is slightly heavier than the salt solution in this vessel underneath. So gravity only pulls down the drop very slightly. Now, as those drops form, well, they are drops. That's to say, the liquid assumes a round form, as if it was like a balloon, a kind of elastic skin round the surface of the liquid that was making it the shape of a round balloon. Mr. Coates will now turn that on, and you will see, as the liquid slowly escapes from the funnel, of course, we're doing it this way, it really happens to when water comes out of a tap, but it goes too fast, you can't see it. By making these nearly the same gravity, it'll fall quite slowly, and you'll see it behaving as if it were liquid enclosed by an elastic skin. Even when it hits the bottom, perhaps you can see that it'll bounce a little bit on the bottom, just like a balloon would. And you can see it wobbling as it goes down. Now, here is a simple experiment to mock up this effect, to show you that the shape the drop takes is that what would be taken by something heavy inside an elastic skin. I've got a skin of rubber here and a pot of mercury. Now, I'm going to pour this very heavy mercury slowly into this skin, and you'll see the rubber will come down and form a drop very much like the oil did in that experiment over there. I'll pour it in slowly. Now, perhaps you can see the rubber beginning to come down. We will not go on to the point where this drops, because we don't want mercury all over the place. There you see it trying to form, and you see a little bit more, and it would contract, and perhaps I put too much in, drop away, like that drop did there. So the liquid behaves as if it had a skin. Now, there's no skin really. The outside of the liquid is just the same as the inside. The reason why it behaves like this and has what we call surface tension, that's the scientific name for this skin effect. The reason is that the molecules are being attracted strongly by each other, and the molecules on the surface are being pulled by their neighbors inside. Those inside, of course, are pulled all ways, but those on the surface feel this strong pull towards the inside of the liquid. And that makes the liquid take up a shape where the outside is as small as possible. And to do that, for instance, a drop turns into a sphere. Here's an analogy which perhaps explains the effect. You've probably seen a flock of sheep with a lively dog keeping them together by nipping the heels of the sheep on the outside. Now, a flock like that behaves as if it had surface tension. It assumes a round or a roundish form, not because there's an elastic band holding the sheep together, but because the sheep on the outside are trying to get inside, aren't they? So that they shan't be nipped by the dog. There's a strong attraction of the middle of a flock for the sheep on the outside. So they assume a form when there's as little outside as possible, as few sheep on the outside as possible for the dog to get at. And this skin can be quite strong. I have here a little sieve. Now, you remember one of the story about the Jumblies, how they went to sea in a sieve, which is always supposed to be such a very stupid thing to do. But this sieve, you see, I can float it on water. You could go to sea in it. Actually, the trick is we've made this sieve a little greasy so the water doesn't wet it. And then the surface skin, which is pressed down by the sieve resting on the water, is quite enough to let it float. There you see it's floating quite happily. It's made of, it's an iron wire sieve. It's floating quite happily on the surface of the water. This same surface tension, this skin, is what pulls a blob of ink up into blotting paper, for instance. It draws it up between the fibers of the paper. This skin depends, the strength of this skin, the surface tension, depends on the nature of the surface. Water has rather exceptionally strong skin. But we can weaken that skin very much if we put a little detergent or oil on the water. In a way we'll see presently, the oil molecules or detergent molecules form a sheet over the water, and that makes the surface tension much less. Very little will do it. We've got 3 red laths here making a triangle. Again, they're held together by surface tension, like little straws are in a stream, which draws up the liquid in the places where they touch. It's pure water inside and out, so the surface tension is the same inside and out. But Mr. Coates has only to put a minute drop of this detergent in the middle, and you will see it'll so weaken the surface of the middle that our 3 laths fly apart. Now, why does the detergent or an oil spread over the surface of water? We've got to think about the structure of the molecule. This is the nature of one of these molecules, illustrated by this model here, very much like the polythene which I showed in another talk. It's a long chain of these carbon and hydrogen atoms, and all this part of it is greasy or oily. It's what you might call an oil-loving and water-hating end. Whereas at the other end of this, just the very end of this molecule, this unit here, I've represented by a red blob, an oxygen or something of that kind, is one which is water-loving. The grand names for them are hydrophilic and hydrophobic, water-loving, water-hating ends. So that this end of the molecule is a water-loving end and tends to stick into the water, whereas this end hates the water and sticks out of it. So you must picture the detergent or the oil, when it's floating on the surface of the water, as a long molecule with a water-loving end burrowing its head into the water and a water-hating end sticking up. And the consequence is, if we take a box of detergent powder and I shake these molecules onto the surface of the water, you will see their water-loving ends all diving in and their water-hating tails all sticking out. And therefore, you see, they all float about like that and formed a kind of raft, as it were, of these molecules, with one end sticking in the water and the wriggly end all sticking out. Now we're ready to explain how a detergent works. I have said that if you just use plain water, it's very easy to wash a jammy plate and very hard to wash a greasy one, because water loves jam, so to speak. They mix, whereas water and oil or grease do not mix. So we put on our plate molecules like this, or these ones that I've got floating here, which are such that their grease-loving ends, all as it were, love the grease on the plate and stick into it, leaving water-loving ends outwards. So we coat the spot of grease, whatever it is, with a coating which has a water-loving, something that will mix with water on the outside surface. So in effect, the detergent turns grease into jam, because it's the surface that matters. The water-loving surface will mix with the water, and we can easily wipe the stuff off the plate. A simple experiment to show that. I've got here a pot of clean water, and floating on the surface of the water is a drop of oil. That oil actually is heavier than the water, but it's floating because the oil is not wetted by the water, so that the water skin runs along under the drop and up the other side. The drop is supported on a kind of spring mattress by this water tension. But if I put a tiny spot of detergent onto that water, now the greasy-loving end of the detergent will stick into the oil drop, coating its top with water-loving ends, water-attracting ends, so now the water can flow right over the top of the drop. There's nothing any longer to hold it up. Here is a little detergent. I'll just put a spot of that now. And you see the drop will fall down to the bottom. Again, you see, we are, as it were, removing that drop of water from the top by adding a little detergent. Finally, oil. You know if a bearing is squeaky, for instance, a bearing on a motor like this, a tiny trace of oil, even a little bit beyond the feather, will miraculously and immediately stop the squeaking. What's happening? How does the oil do that? Well, to see that, we must think a bit about the nature of an oil. Here, this can represent an oil molecule. In this long chain molecule, all this part is quite slithery and slippery. It would represent, say, a part of grease or of paraffin wax or of something of that kind. But at one end, represented by this red ball here, the oil molecule has got a very active unit, an acid unit actually, which has a very strong affinity for a metal, which bonds tightly onto a metal. So when the oil molecules get at the axle of the motor, they immediately spread over the surface of the metal and anchor themselves hard. Each one of them wants to get down to the metal, so they anchor side by side and make a lot of slithery, slippery molecules all anchored to the metal at this end. You know how tremendously slippery a rock can be when it's covered with seaweed. Well, oil is a kind of molecular seaweed, with this as the root and this with the slippery tail sticking out. So, you see, when we oil our motor, we make a layer of seaweed, slippery seaweed over the metal, and there we get no friction. Here is the way we can picture the oil molecule sticking to the metal. This is its active end here, and you see we can think of it like that, with the oil molecule stuck on there and a kind of slippery, slithery tail. Well, now I have a model over here which illustrates this slipping of the oil. We're going to make two surfaces rub over each other, one with a mocked up oil surface on them and the other without. Here is my model of the metal structure. Of course, the surface may look quite smooth and shiny, but when you get right down to the atomic scale, it's full of little valleys and mountains. And as two pieces of metal slide over each other, Mr. Coates has another similar piece of clean metal here. These valleys and mountains stick into each other, they shear bits off, and so there's what we call friction. You see how hard it is for us to push these two over each other. But if Mr. Coates now produces a surface which we've oiled, here it is, we've got over this surface, you see, these oil molecules, firmly attached to that end by their active ends to the surface, and with their paraffin-like, wax-like ends sticking out. Of course, it wouldn't do just to have paraffin wax alone. It's just as slippery, but it has no way of attaching itself to the metal, so it just gets sheared away when the metal slides over the other piece. But now, if we have those seaweed-like things anchored at that end, and now we try to slither them over each other, you see it's quite easy. We've lubricated the metal. It moves quite easily and freely. So you see, there's really a great deal to know about surfaces. Not only are they very interesting scientifically, but they're very important things indeed in our everyday life.